If you're preparing for a networking interview and want to master RSTP quickly, this video is your shortcut. In just a few minutes, you'll learn the most important RSTP questions that interviewers love asking. Let's jump straight into the essentials. 1. What is RSTP in networking? RSTP, or Rapid Spanning Tree Protocol, is an improved version of the original spanning tree protocol designed to achieve faster network convergence. It significantly reduces the time it takes for a network to respond to topology changes by utilizing optimized port roles and states. RSTP is defined in IEEE 802.1W and ensures loop-free Layer 2 network environments efficiently and quickly. 2. How does RSTP differ from traditional STP? RSTP differs from traditional STP by offering dramatically faster convergence through simplified port states and improved handshake mechanisms. Traditional STP relies heavily on timers, while RSTP uses rapid transition processes that minimize delays. Additionally, RSTP introduces new port roles and states to enhance efficiency. This results in near-instant response to topology changes, making modern networks more resilient and responsive. 3. What are the main objectives of RSTP? The main objectives of RSTP include providing a loop-free Layer 2 network, reducing convergence time during network topology changes, and improving overall stability. Unlike STP, which can take up to 50 seconds to converge, RSTP aims to achieve near-instant recovery. It modernizes the logic of STP using faster state transitions and efficient communication between switches, ensuring reliable forwarding paths. 4. Which IEEE standard defines RSTP? RSTP is defined under the IEEE 802.1W standard. This standard enhances the original spanning tree protocol by introducing mechanisms to speed up convergence. The 802.1W standard focuses on optimizing network resiliency and performance by refining port roles, states, and handshake procedures. This improvement ensures that networks can quickly adapt to failures or changes, minimizing downtime and interruptions. 5. What are the port roles in RSTP? RSTP introduces several port roles, including root port, designated port, and alternate port. The root port connects to the root bridge, the designated port forwards traffic toward downstream segments, and the alternate port provides a backup path. These roles help organize forwarding decisions and prevent loops while offering faster convergence compared to traditional STP. 6. What are the port states in RSTP? RSTP simplifies port states to just 3: discarding, learning, and forwarding. The discarding state prevents data forwarding and ensures loops are avoided. The learning state allows MAC address population, while the forwarding state enables full data transmission. This streamlined structure enhances the protocol's ability to react quickly to topology shifts and resume stable network operation. 7. How does RSTP achieve fast convergence? RSTP achieves fast convergence by eliminating timer dependencies and introducing rapid transition mechanisms. It uses handshake processes like proposal and agreement between switches to move ports quickly into forwarding mode. Additionally, it relies on alternate and backup port roles to provide immediate failover paths. This allows RSTP to stabilize networks far more quickly than traditional STP's timer-driven approach. 8. What is the role of the root bridge in RSTP? The root bridge functions as the logical center of the Layer 2 network topology. All switches calculate their best paths to the root bridge and assign port roles accordingly. Although RSTP accelerates network adjustments, it still uses the root bridge concept from STP. The root bridge sends BPDU updates that help maintain consistent network operation. 9. How does RSTP handle BPDU exchanges? In RSTP, all switches generate and send BPDUs every 2 seconds, unlike STP where only the root bridge generates them. This constant communication improves responsiveness. RSTP BPDUs carry additional information enabling rapid transitions and negotiation between ports. The proactive BPDU exchange helps detect changes faster and ensures all switches remain updated to prevent loops. 10. What is a proposal and agreement mechanism in RSTP? The proposal and agreement system is a mechanism used to accelerate convergence. When a switch wants to move a port to forwarding state, it proposes this to the neighboring switch. The neighbor checks for loop safety and, if safe, sends an agreement. This handshake ensures immediate forwarding transitions without waiting for traditional STP timers, dramatically improving network responsiveness. 11. What is an alternate port in RSTP? An alternate port is a backup port that provides an immediate substitute path toward the root bridge if the primary path fails. It remains in discarding state until needed. This role speeds up failover processes by offering precomputed path redundancy. When the active port goes down, the alternate port transitions to forwarding swiftly and seamlessly. 12. What is a backup port in RSTP? A backup port is similar to an alternate port, but is used when multiple ports on the same switch connect to the same segment. One becomes designated and the other becomes backup. The backup port activates only if the designated port fails. This logic ensures the network always has pre-planned safe forwarding paths without recalculation delays. 13. How often does our STP send BPDUS? Our STP sends BPDUS every 2 seconds. Unlike STP, where only the root bridge sends them, every RSTP-enabled switch transmits its own BPDUS. This creates a more dynamic and responsive network environment. The frequent BPDU updates help detect link failures and topology changes immediately, supporting the protocol's rapid convergence goals and ensuring networks adapt efficiently. 14. What happens when an RSTP switch stops receiving BPDUS? If an RSTP switch stops receiving BPDUS, it assumes a topology change may have occurred and begins recalculating the spanning tree. It may promote alternate ports or change port roles to restore connectivity quickly. This proactive response helps our STP maintain high network uptime and avoid loops or outages caused by link failures or neighbor issues. 15. What is the default hello time in our STP? The default hello time in our STP is 2 seconds. This value determines how frequently BPDUS are transmitted. Although configurable, the default interval works efficiently without significantly increasing overhead. The frequent hello messages help maintain consistent communication across switches, enabling immediate topology awareness and contributing to our STP's fast convergence capabilities. 16. What is the forward delay timer in our STP? Our STP technically still includes the forward delay timer for backward compatibility with STP, but the protocol rarely relies on it. Because our STP uses rapid transitions through proposal and agreement, forward delay is not typically applied. This significantly shortens the time ports spend in intermediate states, allowing the network to stabilize almost instantly. 17. What is the max age timer in our STP? The max age timer in our STP remains for compatibility with STP and typically defaults to 20 seconds. It determines how long BPDU information is retained before being discarded. While our STP reduces dependency on timers, max age helps ensure interoperability with STP. Our STP still benefits from this safeguard for maintaining network consistency in mixed environments. 18. Can our STP work with traditional STP? Yes, our STP can interoperate with traditional STP thanks to backward compatibility features. When connected to an STP switch, an RSTP switch automatically downgrades its behavior to match STP. However, convergence becomes slower in such mixed environments because our STP cannot use its rapid transition methods fully. Homogeneous RSTP networks perform significantly better. 19. What are edge ports in our STP? Edge ports are ports connected directly to end devices, such as PCs or printers, rather than switches. They bypass the normal RSTP state negotiation and transition immediately into forwarding, similar to STP's portfast feature. This reduces delays for end devices and enhances user experience by allowing instant connectivity upon link activation or reboot. 20. How do edge ports improve network performance? Edge ports improve performance by avoiding unnecessary spanning tree calculations for device-only links. They transition directly to forwarding, minimizing delays for end-user devices. This prevents disruptions and speeds up workstation connectivity. Additionally, edge ports reduce BPDU overhead by simplifying interactions. If a switch is connected mistakenly, our STP automatically adjusts, preventing loops and maintaining stability. 21. What is the difference between alternate and backup ports? Alternate ports provide an alternative path toward the root bridge from a switch. Backup ports are additional ports on the same switch connecting to the same LAN segment. While both remain in discarding until needed, alternate ports protect against upstream failures, whereas backup ports handle redundancy for segment-level failures. They support faster recovery and efficient loop prevention. 22. Why is our STP considered faster than STP? Our STP is faster because it reduces dependency on timers and leverages rapid handshake transitions. It also uses alternate and backup ports to maintain ready-to-activate paths. Instead of waiting for 30 to 50 seconds like STP, RSTP achieves convergence in a few milliseconds to seconds. These improvements make it ideal for modern, dynamic network environments. 23. What is sync mechanism in RSTP? The sync mechanism ensures that a switch only transitions ports into forwarding when it is confident no loops will form. During synchronization, a switch temporarily blocks non-edge designated ports until receiving agreements from neighbors. This process helps maintain loop-free topology while supporting accelerated convergence. The sync mechanism is crucial for stable, rapid transitions. 24. How does our STP handle topology changes? Our STP responds to topology changes instantly by updating port roles, activating alternate paths, and sending immediate BPDU notifications. It does not rely on topology change timers like STP. Endports do not trigger topology change notifications, reducing unnecessary updates. Our STP's rapid detection and correction restore forwarding paths quickly, minimizing downtime and enhancing performance. 25. What is a topology change notification in RSTP? A topology change notification, TCN, in our STP indicates that a network change has occurred. Unlike STP, our STP embeds TCN information directly within BPDUs. RSTP clears MAC addresses quickly to ensure efficient relearning. Edge ports never generate TCNs, reducing noise. This streamlined method provides faster recovery and maintains accurate forwarding databases with minimal disruption. 26. What are the advantages of RSTP? RSTP offers faster convergence, improved resilience, and simplified port states. It enhances performance by using dynamic BPDUs from all switches, rapid transition mechanisms, and standby port roles. Our STP improves redundancy and minimizes downtime during topology changes. Its backward compatibility with STP also allows gradual network upgrades without breaking operations, making it ideal for evolving infrastructures. 27. What are the disadvantages of RSTP? RSTP may be less efficient in very large networks that require complex topologies. Mixed environments with traditional STP slowdown are STP's benefits. Additionally, improper configuration of edge ports or misinterpretation of rapid transitions can lead to temporary loops. Despite its benefits, our STP may require careful planning and knowledge for optimal performance in enterprise setups. 28. Can our STP be used in large enterprise networks? Our STP can be used in large enterprise networks but may require careful design to avoid scalability issues. While it dramatically enhances convergence, extremely large or complex Layer 2 networks may demand more advanced technologies like MSTP or fabric-based solutions. Our STP is ideal for medium-sized environments where rapid transitions and simplicity are valued. 29. What happens if two RSTP switches disagree on port roles? If two RSTP switches disagree on roles, the proposal and agreement mechanism resolves the conflict. Switches communicate using BPDUs to negotiate loop-free paths. One switch becomes designated or root based on bridge ID and path cost. This negotiation process ensures stable topology alignment. If communication fails, ports temporarily block to avoid loops. 30. How does our STP determine root bridge selection? Our STP follows the same method as STP for root bridge election. The switch with the lowest bridge ID, a combination of priority and MAC address, becomes the root bridge. Our STP accelerates convergence but still respects this fundamental rule. Proper configuration of bridge priority helps shape the intended network structure and control traffic forwarding behavior. 31. What is port priority in RSTP? Port priority helps determine which port becomes the designated or root port. Lower value port priorities are preferred. Combined with path cost and bridge ID, port priority influences our STP decisions during role assignment. Adjusting port priorities allows network engineers to influence convergence behavior and ensure predictable traffic paths across spanning tree topologies. 32. What is path cost in RSTP? Path cost represents the cumulative metric associated with a link toward the root bridge. Higher bandwidth links have lower path costs. RSTP calculates path costs the same way as STP. The best path becomes the root port. Tuning path cost values helps optimize network performance, ensuring efficient forwarding and controlling how traffic flows across links. 33. What is the role of BPDU version in RSTP? BPDU version allows compatibility between RSTP and STP. RSTP uses version 2 BPDUS containing additional fields for rapid negotiation. When RSTP detects STP BPDUS, it reverts to STP mode for compatibility. This adaptability ensures reliable connectivity in mixed environments. Although full RSTP performance requires version 2 BPDUS exclusively across the network. 34. What happens when an RSTP edge port receives ABPDU? When an edge port receives ABPDU, RSTP immediately transitions the port into a non-edge role. It no longer bypasses spanning tree calculations and participates fully in RSTP. This prevents accidental loops caused by incorrect connections. RSTP's automatic detection ensures the network remains stable even if an access port is connected to another switch. 35. How do you configure RSTP on Cisco switches? Configuring RSTP on Cisco switches typically involves enabling it using the spanning tree mode rapid PVST or spanning tree mode RSTP command, depending on the platform. After activation, ports automatically adopt rapid transition mechanisms. Administrators can configure edge ports, port priorities, and path costs. Proper configuration ensures the network benefits from RSTP's fast convergence features. 36. What is Rapid PVST+? Rapid PVST+ is Cisco's proprietary implementation of RSTP that supports per VLAN spanning trees. It offers rapid convergence on each VLAN independently. This provides a high degree of control but consumes more resources because each VLAN gets its own spanning tree instance. Rapid PVST+ optimizes network resilience and flexibility, especially in enterprise networks with multiple VLANs. 37. What is the difference between RSTP and Rapid PVST+? The main difference is that standard RSTP operates as a single spanning tree instance, whereas Rapid PVST+ creates separate rapid spanning trees for each VLAN. Rapid PVST+ offers more granular control and better redundancy per VLAN but requires more processing. RSTP is simpler and more lightweight, suitable for smaller networks or non-VLAN environments. 38. What is Uplink Fast and does RSTP replace it? Uplink Fast is an STP enhancement used to speed up convergence on access layer switches. RSTP replaces Uplink Fast functionality natively by using alternate ports and rapid transitions. Since RSTP inherently provides fast failover, Uplink Fast becomes unnecessary. This simplifies configurations and delivers superior performance without the need for additional STP features. 39. What is Backbone Fast and does RSTP replace it? Backbone Fast was an enhancement for improving convergence through indirect link failure detection in STP. RSTP replaces Backbone Fast as well because its fast detection and BPDU processing eliminate the delays Backbone Fast aimed to improve. With rapid acknowledgement and negotiation mechanisms, RSTP makes backbone recovery far quicker and more efficient. 40. How does RSTP prevent switching loops? RSTP prevents loops by assigning port roles, using discarding states, and implementing rapid handshake mechanisms. It ensures only the necessary ports forward traffic while keeping redundant paths in standby. If a link or port fails, RSTP instantly activates alternate paths. Its continuous BPDU exchanges keep topology awareness high, preventing loops effectively and proactively. 41. What is a point-to-point link in RSTP? A point-to-point link refers to a direct connection between two switches. RSTP identifies these links automatically, allowing faster transitions because they support rapid handshakes. Full duplex links are always considered point-to-point. This enables quicker proposal and agreement processing, leading to near-instant port forwarding and accelerated overall network convergence during topology changes. 42. What is a shared link in RSTP? A shared link involves multiple devices communicating on the same collision domain, such as hubs or half-duplex connections. Our STP treats shared links differently and uses slower transitions because rapid negotiation is not guaranteed. Ports on shared links must follow traditional STP-like behavior. This distinction ensures stability and prevents loops on legacy network segments. 43. What is route path cost in RSTP? Route path cost is the total path cost from a switch to the route bridge. Our STP uses this value to determine route port selection. Lower path costs indicate better routes. Our STP calculates these costs dynamically and updates them quickly when topology changes occur. Proper adjustment of path costs ensures optimal traffic forwarding and redundancy planning. 44. What is port synchronization in RSTP? Port synchronization ensures that all non-edge designated ports are placed in a safe state before a new forwarding decision is made. During synchronization, the proposing switch temporarily blocks certain ports to prevent loops. Once agreement is received from neighbors, ports transition rapidly. This mechanism ensures both stability and speed in the convergence process. 45. How does our STP improve reliability? Our STP improves reliability by maintaining alternate and backup paths, allowing immediate failover. Its rapid detection and response mechanisms minimize network disruption. Frequent BPDU updates enhance awareness and prevent stale information from causing issues. Our STP's efficient negotiation takes advantage of modern full duplex networks and ensures consistent performance even during unexpected failures or configuration changes. 46. Does our STP need manual tuning to work efficiently? Our STP works efficiently by default, but manual tuning helps optimize performance. Adjustments may include configuring edge ports, setting port priorities, and modifying path costs. Proper tuning ensures predictable traffic patterns and faster failover. While not required, thoughtful configuration enhances network stability and maximizes our STP's benefits in larger or more complex environments. 47. What happens if the route bridge fails in RSTP? If the route bridge fails, our STP quickly elects a new route bridge by evaluating BPDUs from remaining switches. Alternate paths become active almost instantly, ensuring minimal disruption. Because our STP does not depend heavily on timers, recovery occurs much faster than STP. This quick transition keeps traffic flowing efficiently even during major topology disruptions. 48. Why should organizations use our STP today? Organizations should use our STP because it provides a balance of reliability, speed, and simplicity. It is ideal for modern networks needing rapid convergence without migrating to more complex technologies. Our STP's backward compatibility and minimal configuration effort make it practical for environments transitioning from older STP designs. It strengthens network resilience and ensures smooth operations. Thanks for watching. I hope this video helped you better understand our STP and prepared you for your upcoming networking interview. If you found this content useful, don't forget to like, share, and subscribe for more in-depth IT and networking tutorials. Your support helps the channel grow and lets us continue creating valuable content for learners around the world. See you in the next video.